All right, let's get started on time so that we don't get delayed with lunch as well. My name is Li Xi. I'm going to chair this session in introducing to you two excellent invited speakers. The first one will be Jakub Sistek from the Institute of Mathematics and of the Czech Academy of Sciences.
Okay, thank you very much for the introduction. Good morning, ladies and gentlemen. First of all, let me thank the organizers for inviting me. It's really a great honor to be here and to present some 20 years of work, collaborative work with my colleague Václav Kolář from the Czech Academy of Sciences. Who, I have the feeling that the invitation was meant for him, and he should stand here instead of me due to his large amount of work in the field. Unfortunately, he retired last year, and he wasn't able to join today. But it was him who brought me to the area of vortex identification methods, and everything I'll present are mainly his results today. I'll give an overview at the beginning of some of the work, and I'll finish with some two new proposals to quantities based on eigen-based geometric properties of a vortex. This is the outline of my talk. I'll start with brief motivation. I'll give some overview of the historic evolution of local region type vortex identification methods. I will present the two recent papers that we've published on orbital compactness of vortices, compact and loose regions, and on local axisymmetry of vortices and cylindricity of vortices. I'll present the software that we are developing and close with some summaries. So I believe there's not much need to speak about motivation for identifying vortices in flows at this conference, in this group. So we all know it's very important. There are key questions. First, what is a vortex? And then how to define it mathematically. While I think everyone here has some intuition about the first question, I think the second one is much more challenging, and I don't think we are near finding a conclusive answer, to be honest, because pretty much every method around has some pros and cons, and so there's no universally accepted method that would fit all the cases and that would fit all the needs that I believe we need. In particular for local methods, one key question, as introduced by Professor Liu, is to distinguish between what is shearing and what is rigid body rotation, pretty much this decomposition of vorticity. And I also have an example here. So if this is a two-dimensional case, 2D flow behind an airfoil, a simple airfoil, so this is what vorticity field looks like. Obviously, if you plot stream traces, there's nothing to do with vortices. That's the shear layer as introduced. You can do better if you split it to what Václav Kolář introduced as residual vorticity. You get closer to the vortices if you look at the stream traces. So you almost hit the center. I have to say that we have seen cases where you don't fit exactly the centers. So here I still believe stream traces has something to say, because I see some inherent limitations to these local methods. So it's not only the center of the vortex that has a high value of the residual vorticity. So some biased overview, I have to say biased overview of local region type methods. I apologize to everyone working in the field having his method that I won't mention, but maybe the important questions. Okay, now there's some feedback, I don't know. Okay, anyway, today I'll speak about Eulerian methods, and we are focusing on local methods based on velocity gradient, pretty much. And then these split into region type schemes. The rest of my talk will be about these schemes, whereas there are these line type schemes that search for the vortex core skeleton, as also mentioned, and my colleague Marek Pátý will speak about the method for this type of identification of vortices. As for the basics, so we all know about the splitting of the velocity gradient into symmetric and non-symmetric part, which is strain rate tensor and vorticity tensor. Okay, can we do something about it? Ask more times. Is it better?
Yeah, I think it's...
Thank you. Is it solved?
I close the speaker of this.
Okay, I think it's better. Yes.
Oh, okay. Yeah, because that's the speaker. Yeah. Okay.
Okay, this one. Perfect, thank you. I'll jump there quickly. So S is the strain rate tensor, obviously. Omega is the vorticity tensor. And there's a clear link between the vorticity tensor and vorticity vector, as we know. You can identify the vector and the tensor omega here. I'll start my overview with the well-known Q criterion from 1988, saying let vortex be the region of fluid where we have positive second invariant of the velocity gradient. So it's this term. If you consider incompressible flows, then this trace here is zero, and it becomes this one, which then can be expressed in this way, which we like to read as the region where vorticity magnitude dominates over the strain rate magnitude, right? So, but it's this equality that's valid only for incompressible flows, although I've seen people using Q criterion in this form even for compressible flows. I have to be honest here. Václav published some years ago a correction valid for compressible flows, and it's simply based on using the deviatoric part of the strain rate tensor here. So the deviatoric part, if you have compressibility effect, then this matrix has a non-zero trace, and you make it zero trace or deviatoric by subtracting the trace, as we know. So it's a slight motivation using this deviatoric part here. The well-known method, other well-known method is lambda 2 method. I'm really honored to present lambda 2 in front of Professor Hussain, one of the authors of the method from 1995. It's based on different idea. The idea to get an approximation of the pressure Hessian using this S square plus omega square, these two matrices. This is a symmetric matrix, so it has 3 real eigenvalues, and if you order them, and then you require, if you are in if there's local minima in certain plane, you need to have 2 of them negative. That corresponds to the local minima. So if they are ordered, it's the second one that matters. It's also derived from incompressible Navier-Stokes equations, although I've seen also lambda 2 being used for compressible flows. The original paper on the identification of a vortex has been cited more than 8,500 times. So as far as I know, this is one of the most influential papers in the field of vortex identification. Say that yet another idea how to define a vortex is this well-known analysis of the eigenvalues of velocity gradient tensor. So this starts with the delta criterion, the different authors, and the idea is so we are speaking about 3x3 matrix of real numbers, the velocity gradient. So there are only 2 options. Either it has 3 real eigenvalues, or there's a real eigenvalue and a complex conjugate pair of eigenvalues. So there are 2 cases. And this family of criterion says, let vortex be the region where we have this complex pair. And the simplest criterion is when we have it, so it's the delta criterion, which stands for the discriminant of this cubic characteristic equation. And if it's positive, we have this complex eigenvalues, and we call this region as complex domain. And I will use the term later. A refinement of this criterion is the swirling strength, another well-known criterion which looks at the magnitude of the imaginary part of this complex eigenvalue and says this has a meaning of angular velocity, and the larger the imaginary part, the stronger the swirling. So that's why string length strength. It has obviously the same zero isocontour. So if you see it as a criterion, then it corresponds to the delta criterion. Another idea was brought by Václav some 20 years ago, and so we have already heard that the double recomposition has this limitation that both parts of the strain rate tensor and vorticity tensor are partly introduced by shear. And Václav Kolář came with the idea of triple decomposition in 2007, decomposing the velocity gradient into 3 rather than 2 parts to identify the shear part of the velocity gradient, and then the remaining residual part to split into residual strain rate and residual vorticity tensor. Obviously, if you take the residual vorticity tensor, it can be made into vector index correspondence that I mentioned for the vorticity itself. To some ideas behind the triple decomposition method, the key idea was to define an asymmetric matrix A. There are some examples of how the structure of this matrix A may look like, and that's a pure shear tensor. And then if you identify the effect of shear, then you can simply define the residual tensor by subtracting it and to divide the residual tensor into this symmetric and non-symmetric part. It provides very good vortex identification results. We are very happy with the method, and we kind of use it as a reference method for many years now. It has a drawback though, and there's no analytical formula to define the basic reference frame where the effect of shear is maximized. So the definition in 3D is complicated. It defines the coordinate system where to perform this splitting using an optimization problem in each point, and that makes the method quite time consuming. So we are using, at the moment, because it's independent and pointwise method, we are using a lot of GPU computing to compute this method. So, but we are still speaking about several minutes to evaluate a reasonably sized flow field in this method. So obviously we have tried to make the method cheaper, and the way to look at it was to look at two-dimensional problem, or the triple decomposition in a plane, and there's the concept of corrotation of line segments. So if you look at the line segments at a point, so if they all rotate, this is the, say, lowest angular velocity, highest angular velocity. By the way, the usual vorticity is the average angular vorticity, average angular velocity, sorry. If they all corrotate, then the residual vorticity is non-zero, and it corresponds to the lowest angular velocity. If there are some opposite rotation, it's like contra-rotation case, then the residual vorticity is 0. So these are the formulas. In 2D, we have simple formulas that are immediate to evaluate. So if it's simple to do it in plane, we were trying to come up with a vector that would correspond to a plane. The problem here is which plane to take. So we are trying to cut the flow field, three-dimensional flow field, by a plane and evaluate the 2D residual vorticity. At the beginning, we tried some experiments with maximizing this value, but it didn't lead to a very robust method. In this plane, given by a normal of the plane, we evaluate the 2D residual vorticity and define a 3D vector from that. And then a more successful approach, an approach I really like a lot now is to average the effect of, or this vector over all the possible planes cutting through the point. For that, we reformulate the problem of all the planes as all the tangential planes of a unit sphere and take its normal. And in fact, the averaging of the effect of this vector becomes a problem of integrating a surface integral on a sphere. Unit sphere is you scale it properly so that you reproduce the vector. It works like projections of an unknown vector into the different normal directions. And this is again a vector by construction that we call average corrotation of line segments. And we've been using this method a lot since our paper on the topic in 2013. Yes, it's way cheaper than the residual vorticity formulated in this optimization problem. The last method in my overview is the Liutex method that we've heard a lot about in the morning, that has been developed by Professor Liu here at Arlington. This is the formula for Liutex that we've also seen. I think the nice idea about Liutex is that it gives the direction of the real eigenvector of the velocity gradient. In the case we have the complex conjugate pair, so it only works in the complex domain. It's extended by zero naturally elsewhere. Interestingly, in 2D it coincides with residual vorticity. So this method kind of solves also the problem which plane to take to evaluate the residual vorticity in. This takes the plane perpendicular to the real eigenvector. And then in 3D, it takes the plane, but then the magnitude coincides with the residual vorticity in the plane. So it's really 2D residual vorticity magnitude with the direction of the real eigenvector. And it has a lot of similarities with the swirling strength criterion. We have studied this a little bit in these papers, also looking at some of the weaknesses inherited from the swirling strength criterion, which are kind of studied in literature and quite well known. So now to the new results. So the first is on orbitally compact and loose vortex regions. In this paper, we start from this eigen decomposition of the velocity gradient. So again, we will be limited to the complex domain. And so if this is the matrix of eigenvectors, unit eigenvectors and eigenvalues. These eigenvalues are used to define what we call an orbital compactness sigma, and the matrix of eigenvectors is used to define the cylindricity tau, and it was published in this paper recently. So the idea of compactness is not new. It has been introduced for incompressible flows, and it requires that separation of swirling material points inside the vortex is bounded and remains small. So the rate, yes, the stretching changes the real part of the complex eigenvalue, and rotation changes the imaginary part of the complex eigenvalue. And I should also mention that the meaning of the swirling strength is the angular velocity, because the period of if you look locally at the swirling streamline, you can approximate it as in this important paper that has inspired us a lot from 2005. You can view it as angular velocity here. And it was this paper where they studied the effect of stretching. And for incompressible flows, this stretching in radial direction, which is translated into this lambda CR, the real part of the complex eigenvalue, or axial stretching, which is the real eigenvalue, they are connected through this incompressibility condition, zero trace. They are connected together. They need to fulfill this, condition. And the inverse orbital compactness introduced in this paper, the authors proposed to limit this important factor, this real part of the complex eigenvalue over the imaginary part of the complex eigenvalue by certain threshold deltas, so that you don't allow a very large stretching in your vortex. I think I'll go quickly here. If you recall the characteristic equation of an velocity gradient g, here denoted as g, you have these three invariants, trace, the second invariant, and the third, which is determinant. You can use the trace, the deviatoric form of the gradient, and since this is the trace, which is 0 for deviatoric gradient, you end up with this form. And an important matrix to look at here is this g squared, or g times g. If you look at its trace, you can formulate it using this trace of g, which is squared. And this squaring is a problem here, and although this provides the basis for the new compactness that would be valid for compressible flows, it's not sufficient. So some other considerations are as follows. So for compressible flows, you cannot consider this condition doesn't hold, but you want to take into effect, say, pure volumetric deformation like contraction, compression, or expansion. Expansion has a positive trace, compression a negative trace, and in this pure case they would coincide. So all the real parts would be the same. You don't want if it's a geometric property, you don't want to be proportional on lambda ci, because the compactness should be valid both for strong and weak vortices. And the key idea here was that this quadratic form, this trace squared, cannot really distinguish between expansion and compression. So it ignores the effect, whereas the intuitive way would be that compression helps the compactness, whereas expansion weakens it. So that's kind of why we considered this thing. So this is the final form of the compactness, orbital compactness sigma, which has a deviatoric part here based on the eigenvalues. I won't comment it that much. And then this correction due to this compressibility effect that takes into account this the compression makes the compactness stronger, whereas expansion weakens it. So that's pretty much the meaning of this correction term here. I like this plot that we've presented. It's a plot given the axis of real eigenvalue over the imaginary part of the complex eigenvalue, and real eigenvalue, or real part of the complex eigenvalue over the imaginary part of the complex eigenvalue. In this plot, this blue line corresponds to incompressible flow due to this condition lambda r equals -2 lambda cr. Over here is expanding part, down the blue line is compression. So if you don't consider the correction due to compression, you would end up having this dotted band as compact vortices. If you consider also the compression part, the trace, in the expansion period, you make it smaller, whereas the area of compact vortices expands in the compression region. These are 4 flow cases that we've tested the method on. This is flow around a sphere, around a plate, then one vortex from the boundary layer transition, and a reconnection process of 2 Burgess vortices. And on these 4 cases, we've evaluated 5 vortex identification methods, and we looked at what part of the identified vortex corresponds to compact region and what corresponds to loose region. So Q is compact by definition. It's a very strict criterion, 100% in compact zone, lambda 2, large part compact, some loose. The residual vorticity is showing a lot of compact, but also a lot of loose region. This vortex and lambda CI can show a large part of the vortex as loose region, in fact, evaluated using this compactness. And if we speak about loose, it can be really loose. I have an example of a logarithmic spiral here with a growth corresponding to this ratio of lambda CR over lambda CI. And we define the compact vortices as those that for sigma larger than 0. So we still, even if this ratio is 12 times higher, we still call it compact. So even if it does just like it almost don't revolve, it's still called compact. So it's interesting to see how fast the stretching can be to still call the vortex compact. In my last time, I will briefly mention the concept of cylindricity of a vortex. They started with an interesting observation from a paper by Chong and others from 1990, which states that a vortex core is a region of space where the vorticity is sufficiently strong to cause the rate of strain tensor to be dominated by the rotation tensor. That is, the rate of deformation tensor has complex eigenvalues. So if you read carefully, this sounds like the Q criterion, whereas this is the delta criterion, and it sounds like Q is a necessary condition, or the Q criterion is a necessary condition to have complex eigenvalues for delta criterion. And actually this is not true. We have in this paper we formulated counterexamples and what is behind them, what sort of counterexamples is behind them. We've considered this form of tensor of velocity gradient. This is same as here. If it's minus, it will be 2 times plus 2 times that here, and then omega here. And even in the case of very large strain rate here, and very small but non-zero omega, you can evaluate the delta criterion, the discriminant of the cubic equation, to see that you will have, it's positive and you will have complex eigenvalues. And the key behind that is that this submatrix is axisymmetric, and it translates directly to this real part of the complex eigenvalue and the imaginary part of the complex eigenvalue. These parts here can be the added shear, so they are ignored here. Regardless of this shear part, you will have complex eigenvalues. So I will skip here. We analyzed, if you consider zeros here, this would be a velocity gradient that we would call a perfect cylindricity of the flow field. So it's axially symmetric in 3D. If you, on the other hand, consider more general velocity gradient and you analyze this matrix, if it's zero, if the matrix is zero, then these terms turn out to be zero matrix, or you have this term, and such G in linear algebra we call this form of matrix normal. And if it's normal, it has a set of orthonormal eigenvectors. So it's actually the angles between the unit eigenvectors that are important for the cylindricity. So if you have a cylindric velocity gradient, you may have very low vorticity and still qualify for the complex domain. That's the takeaway message, so to say. So we've proposed the measure of cylindricity, taking the matrix of unit eigenvectors, computing its determinant, taking its absolute value. It can range from 0, which is like no cylindricity, to 1, which is corresponding to orthogonal eigenbasis and perfect cylindricity. Here, to summarize these two concepts, we have this eigendecomposition, and from eigenvalues we take the orbital compactness, from eigenvectors the cylindricity and 2D axis symmetry. Both are defined only for complex domain, naturally, for complex vectors, and the compressibility only affects the compactness. They are mutually independent. You can have cases where you have compact vortices and high or small cylindricity, so that is the top row is with 0, bottom row with non-zeros. So here you have loose vortices. That's like the streamline at the point, like approximation of the streamline. This would be loose but cylindric, and this would be loose and with low cylindricity and at this end. These are again the 4 flow cases, and in these we plot the 0.5 surface of the compactness and 0.5 surface of the cylindricity. So this is lambda swirling strength with very small threshold. We see this as an approximation of this complex domain. So everything interesting happens inside of these domains. You can see that these two contribute to this somehow, both, but different regions. So this cylindricity is may be in different regions than when the flow is compact. If you look at the, say, Q criterion and lambda 2 for certain thresholds, you can see that these are the swirling strength independent. So they show more these geometric values can be shown also in weaker vortices than these criteria tend to show. So we abstracted from the notion of strength. We've implemented these into a collection of routines for computing with this vortex identification criteria that we called VA-lib, Vortex Analysis Library. It's C headers, so they are usable from C, C++. We have Fortran bindings, and we use them a lot for GPUs from CUDA and HIP. And to summarize, I've presented 2 complementary eigen-based geometric properties of a vortex. They are applicable to a range of flows, even compressible, and they can provide some restriction to the overly tolerant complex domain criteria. As for the outlook, I think it would be interesting to make a proper comparison of the vectorial vortex identification methods like residual vorticity, average corrotation, and Liotex. If you are interested, these are the 2 papers I've been referring to, and with that, I thank you for your attention.